Section 13.2, chemical equilibrium. So in the last section we talked about rates of reactions. We said some reactions happen fast, some reactions happen slow. And we're going to take a look at those rates, how fast it's occurring, because at a certain point we can have a reversible reaction where the rate is the same for the forward as it is for the reverse. So first let's talk about what a reversible reaction is. Basically, it's a reaction that goes backwards and forwards. So let's take a look at this A right here, and I'm just going to write it a couple different ways. So the first way I'm going to write it is that the nitrogen gas plus 3 hydrogen gas, that goes to form, notice that it's a one-way arrow, that goes to form 2 ammonia gases. Okay, so we have that reaction. But we also have this reaction. The 2 ammonia gases are breaking down to form 3 hydrogens and 1 nitrogen. So we have reaction 1 and reaction 2 occurring at the same time. That's what a reversible reaction is. So instead of writing both reactions like that, we just do another arrow beneath it showing the opposite direction. Okay? So when that happens, when we have one of these reversible reactions where we have reactants and products that exist at the same time, not just products like what we've seen up until now, we actually have 2 different reaction rates. There's a forward rate and a reverse rate. Okay? Initially, the forward rate is pretty fast because we have only reactants. And so initially we only have nitrogen and hydrogen typically, and so the forward reaction happens pretty fast. The reverse reaction starts out slow, but it picks up pace. Now, when these 2 rates are equal, so when the reaction rates are equal, we have what is called equilibrium. Okay, and that's very important to note. Equilibrium is when the forward and the reverse reaction rate are equal. So here's a graph showing you reaction rate, and we can see the forward reaction rate starts out pretty fast. The reverse reaction rate starts out at 0. And the reason why it starts out at 0 is because we have no product at first. So we have no ammonia at first. That's why it starts out at 0. We form some ammonia, and then the rate speeds up, and at a certain point the forward and the reverse rate are equal to each other. Now at that point, when the forward and the reverse rates are equal to each other, the concentration of the reactants and the concentration of the products no longer change. But that doesn't mean they have to be equal. So here we can see we've reached equilibrium because the products are no longer changing, and this is molarity, which is concentration. The reactants are no longer changing. And so we have reached equilibrium. So we're looking for 2 things for equilibrium. We're looking for a position where the forward and the reverse reaction rate are equal, and we're looking for a situation where the concentrations are equal, or concentrations do not change. My goodness, I can't believe I just said that. So again, the reaction rates have to be equal, but the concentrations no longer change. That's when we've reached equilibrium. So here, let's take a look. We have hydrogen and iodine, and we're going to form hydrogen iodide. Okay, so here you can see we have 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 iodines, and the forward rate, you can see by the large arrow, which is a large vector arrow, that's pretty big. We form 1, 2 hydrogen iodides, and so now that we've formed 2 hydrogen iodides, we can start having the reverse reaction. Once we form more hydrogen iodides, we can have an even larger reverse reaction rate. And then you can see at point D here, the rates are equal. Equilibrium. Here's sort of the same idea. Sulfur dioxide and oxygen, which is going to form SO3. So there's the SO3. You can see it. And then over here, if we have initially just SO3, we'll go on to form SO2 and oxygen. Alright, so we can go forwards, we can go reverse, doesn't matter. Alright, so that's That's the concept of equilibrium.